Oh. So I'm going to talk about the bar resolution today. I'm not going to assume you know anything. My ring is commutative, and it's probably local or graded, and modules are finitely generated. You get finite, so you get valuable invariance for the singularity that corresponds to the ring that you have from free resolutions. Okay, and there's sort of two kinds of things you can get. So let me just draw a fake little resolution here. F2, F1, F0, M0. If you're graded, you can get even more finer invariance and so on. So all the ranks in here, what the maps are, derived functors you can define from this, everything. So if it's minimal, so these can be minimal resolutions. So if they're minimal, you can usually read invariance straight off from the resolution. It's telling you something directly because the minimal resolution is unique. Okay? So you get, so if it's a minimal, you get it directly. Okay? But of course, some invariance you get from derived cohomologies, homology and cohomology, and then you don't need a minimal resolution. So what you might want to do instead, because these are hard to find and very particular, is instead to look at universal resolutions. Not only do they kind of exist more often, and you could just write them down and maybe use them more easily, they're also functorial, therefore, often. And then sometimes you can see trends over all modules over this ring or something, because you can see them in these universal resolutions that you might not see for minimal, because they're all different, very different for each thing. All right, so I want to talk more about the second half of this today, about some universal resolutions. So the Ur example of a minimal resolution, well, one of the Ur examples of a minimal resolution is the bar resolution. This goes back to Eilenberg and McLean. In 53, amazingly. And this was a breakthrough to compute derived functors of things you care about in representation theory of finite groups, say. So things like modules of invariance and co-invariance. So to compute group, homology, given a group for a group G. So that would be X. So I'm going to do this over Z. X over ZG, the group ring of Z comma Z. So all these X modules, and they're sort of the derived, so these are derived versions of, so this one, you could also put a Tor, but I'll do this one. I think that's usually up. I'm confused because I put upper G in my notes, but it doesn't sound right, but whatever. Oh, so instead of Z, I could put any G module M here. And so Hom ZM, this is giving the co-invariance. So these are the derived functors of that. And so in order to compute these, they defined a sort of universal, it didn't matter what the group was, a universal resolution of Z over ZG, which is the group ring of the group. And you could change the Z to fields or Z mod something, whatever you want. Okay, so that's the bar resolution, which I'm going to start explaining now. So instead of having ZG and Z, I'm just going to take any algebra A over anything K. Over any K. Oh, bad. Oh, there it is. Okay, so immediately people saw that you could take for any A, which is a projective K algebra, meaning it's a K algebra that's projective as a K module. So, you know, this was ZG, and this was Z in the example above. You can do a thing that's called the bar construction, which is not quite the resolution yet. but I want to show you kind of how this leads to the resolution, or the bar complex, or people call it different things. So what it looks like is, so I'm gonna only this time put a lot of tensor factors. So let me put 4 tensor factors down, then 3 tensor factors of A, then 2 tensor factors of A, and then 1. And all the tensors here are over this base ring K. All right. And the differentials are, so an element A1 tensor A2 goes to the product. This is surjective because you could take A1 to B1. Okay. But then the question is, what's the kernel? What are the cycles here? So what's some stuff that goes to 0? Well, if you do, which order did I want? Whatever. A tensor BC, that goes to ABC for any elements in the ring. And so does AB tensor C, that also goes to ABC. So if you subtract these, it goes to 0. And that's why? Associativity. I invisibly didn't put any parentheses. So because of associativity, this is a cycle. So there's a cycle expressing only associativity, nothing interesting about the algebra. Just because of associativity, you have these kind of cycles. And so over here, we want stuff to hit them. So indeed, you take A tensor B tensor C, and you send it to that. So that's actually the definition of the next map. Okay? And so in this way, you actually catch all the cycles at every point. And this is exact. And so let me introduce a little bit of notation. Instead of writing all these tensor products, we'll write this as A bracket BC minus AB bracket C. So the first one I'm putting out separately. So this one I'm going to write as A bracket BC. And so these, just putting bars instead of tensors between all the factors, except the first factors in front. All right. So now I'm going to sort of, as was probably noticed in my notation, I'm going to separate the first factor out and put the others together. Oops. Okay, first factor is, so there are about 10 ways to introduce the bar resolution, and I had to choose one. I started giving up and just, okay. So this is exact. So this is kind of a universal resolution of something. So if you kind of cut it off here, it's exact. So it's a universal resolution of A over A, or it's a universal resolution of A over A tensor A, which acts on the outside factors. So, but that's not the one we care about, but I'll just mention it anyway. This is exact. So this does give a resolution of A over A, the enveloping algebra AE, which is A tensor A. But that is not the topic of today. So instead, we're going to go to, we're going to reduce it a bit. So if the algebra A is augmented, which just means that not only do you have A going to its residue field, but you have not only do you have K sitting inside of A, you have A going to, there's a map from A back to K, and we want that to be at identity. Then you can replace, so a lot of these products are kind of stupid. When the inner factors have a unit, like if you're taking the identity element in A and multiplying it, a lot of the maps are kind of like identity maps if you pick the right basis. So those parts of the complex are contractible and split out. So what we're going to do is replace all the A's in green brackets by a sort of reduced version, A bar, which is the kernel of A going to K. So it's okay. Just think about a graded K algebra whose degree 0 piece is K. You got rid of the degree 0 piece. Yes.
If the algebra happens to be commutative,
yes. A tensor B, very good question. So his question is, I'm going to erase this example. His question is, what about A tensor B and B tensor A, which go to the same thing? Also,
Say commutative, but it might have.
let's say it's commutative. Oh, well, yeah, I didn't say A was commutative. That's true. Okay, let's say A is commutative. Then this is also, this difference goes to 0. So, but why is this coming in the image of this? Is you can write it in several steps going between here and here. This enables you to kind of move things across the tensor. So essentially, A tensor B minus A B tensor 1 and plus A B tensor 1. Yeah, minus. Plus minus B tensor A. And then each of these is in the image of the previous. All right, any other questions? All right. Something like that. Okay. So anyway, this lovely canonical resolution got a little smaller if we get rid of this contractible part. But what I didn't say is at the very end, it actually messed things up. So it got rid of exactly the thing that was helping make it surjective. So in fact, if you do that, so I'm just gonna go. Okay, fine, I'll write it again. So this is called BAAK, which you'll understand why in a little bit. So dot, 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 I'll just put a few of those factors. So if I have A tensor A bar goes to A tensor A bar goes to A. That's gotten rid of most of the homology. I'm sorry, the contractible part, which was not contributing. Oops, these. But it's a bit of a problem here because it's no longer surjective because we have just a, suppose your algebra has K in degree 0 and that's the entire, or then essentially you got rid of the units. So this product only lands in, say, the maximal ideal. And so essentially this, well, A bar is the kernel of A goes to K. So essentially you're left with the kernel of A goes to K because you got rid of the rest. All right, so now this is more of a resolution of K instead. Okay, and then you notice that since A has been taken projective over K, that implies that this is split exact over K. Well, this exact part I'm not explaining. So that's split exact over K. And so I could tensor it with anything I want, and it will still be exact. So now take what's called BAAM. Sometimes it's just called BAM. Sorry, there are 100 different names. And so that's this thing, tensor. So BAAK, tensor over K with M. And since this thing is contractible over K, this thing is still exact. And so if you write it out, you get free modules. I'm going to write it out. And then the last term is M. So let me do that. Then I'll give it names and make some remarks. So, okay, so we get, all right, so I don't know. So you have A tensor over K with all these A bar factors. Suppose there are N of them at some point. And now I've gone and tensored this with M on the right. Okay. And then in every stage, it looks like that. And at the very end of it, it looks like A tensor A bar, tensor M, all the tensors are over K. And then the very last thing is this lovely K sitting here. So I have to tensor, oh no, I have another factor, I missed this term. A tensor with M, and then I have K tensor M goes to 0, so this is M. And these are all free A modules. Why? This is a vector space over K, so it's a direct sum of K's. And then you changed rings up to A, so now it's a free A module. This is also a vector space over K. And you've changed rings up to A, and so on, vector space. So this is a resolution. Okay, so actually let me write the word bar. This is the bar resolution of M. So it's with free A modules. Okay. So now you believe me that this is a resolution, right? Okay. It's lovely because you just write it, you know nothing about M, you know nothing about A, and you get this. It's a resolution. So, okay, you can use it. It's huge. Look, here's what we're resolving. Let's look at the first free module. Okay, so this thing here this is the free A module. So what it is A tensor over K with K to the, what's the vector space dimension of M? I don't know what it is, but I'll write dim Km. Okay, so that's really like A to the dim Km. So it's like a vector space of huge dimension. What's the vector? Okay, I'm pretending K is a field for a second. That's why I keep saying vector space. So the vector space dimension of the module you're resolving is probably enormous unless we have a finitely generated algebra, but we don't. And so this is way too big. You would never start a resolution like this, but it's canonical. Okay, so I will get to that in a minute, how to fix that. What else I wanted to say was, this was used for years in many places. It also works more generally for A equal to a DG algebra, which I will define later in the talk, and M a DGA module. Then you're resolving this DGA module M, right? Which, okay, so this probably first occurred in Carton's seminar. You could also see McLean's book. And anyway, that's been around since also the 50s, that you could do that. But then you're just resolving this DG algebra, which maybe who knows what it is. I mean, DG module, and who knows if you're interested. And again, what's so special about this is that it's canonical. It sort of uses nothing about, I mean, it really uses nothing about A and M. You don't know what the relations of M are. You don't know what the relations of the ring are, right? So you may need to know the dimensions, but you don't need to know the relations of the ring. You have the whole thing. Okay. Well, no, I didn't want to. Thank you. I kept half of it. Okay. So, all right. So this was insert one. Let me put this back. Oh my goodness. What have I done? X2, Y0. Oh boy. X1, Y2, X1, Y1, X1, Y0. Probably Y2, Y1, Y0, Y3, and Y4. Okay, we'll get to that in a second. All right, so to deal with this problem, Shrikant came along and has a very pretty solution, how to make things smaller. All right, so namely, I need to first tell you the ingredients for his result. Okay, so what is a DG algebra and what is a DG module? So, fine. So what you let me actually motivate this. I was just going to give these definitions, but let me start with, let R be Q mod I, and let M be an R module. Okay, and so instead of putting the ring and the modules here, he replaces them with some kind of special resolutions so that, and tensors over something else. So let me tell you. So he's going to resolve R by a Q-free resolution. So that's a Q-free resolution. And he's going to resolve M also over Q-free resolution. So maybe I'll put a dot for now because they're like complexes, but I'm going to stop writing dots. So we have two resolutions. And for his construction, you also need to have a bar-like thing where you're multiplying things together. Remember, the bar differentials were multiplying adjacent elements together. So he needs product structures on these things. So let me recall the definition of a DG algebra and a DG module. So very quickly, a complex X dot of, let's say, Q modules. Also, please stop me whenever you have a question. You might have to shout to stop me. Okay. A complex of Q modules is a DG algebra, which we can abbreviate DGA. And the DG stands for differential because it's a complex and it has a differential, internal differential, and algebra because I'm going to tell you how to multiply it. So it's a differential graded algebra. If there exists a graded multiplication on X tensor X dot goes to X dot, meaning if you have something of degree I times something of degree J, it should land in degree I plus J. So that's the graded product. Let's call it, no, let's not call it mu. Let's not call it anything such that, fine, let me call it M, such that two things are true. One is that it's a chain map. M is a chain map, which is the same as the Leibniz rule, which is like a product rule kind of thing, which I'm not going to talk about. And altogether, this forms a ring. So the direct sum of all the xi's, I bigger than or equal to 0, forms a ring, is a ring. With unit, so with unit with 1 and sitting in degree 0. And I think I only want non-negative degrees, although if you localize, you might want to consider more general DG algebras. Okay, some people, so we're also going to have this be kind of commutative up to sign, and some people call those CDGAs for commutative DG algebra. But I'm just gonna not talk about it a lot. And so the question is like, when do you, okay, so now we have a product on X, which we're going to put into the bar complex, and it will have products, so we can define a differential, bar type differential on it. But you know, when you take this resolution, does it ever have this structure? Can you put a multiplication on a resolution of a ring? So you kind of can, almost, always. So, all right, so if you have X dot is a resolution of the ring R by free Q, this means X is a resolution of R over Q by Q free, the free resolution of R over Q. You can always, you have a product in R, you can always lift the multiplication in R as follows. So you have multiplication in R, let's call it M. Then you have X is the resolution of R, so I have a map from the complex to R. And therefore I also have a map from X tensor X to R tensor R. So I have all these maps of complexes. This one might not be exact because you tensored, it now has Tor modules. Or, you know, the homology here is Tor QRR. I've taken a resolution of R, tensor with a resolution of R, homology is Tor. not exact, but it's projective. This one, on the other hand, is exact or acyclic, has no homology. So by comparison theorem, you always do get that there exists a map here, right? And you're like, great, I have a product. What is wrong with this product? It satisfies everything you want, except one thing that we always forget to think about for rings, which is associativity. Like we never check that because our rings come naturally usually, right? Associativity is not automatic for this. In fact, often not. Doesn't. So we could always lift it, but cannot guarantee. Not guarantee associativity. Okay, so it's actually quite hard to figure out if something has a DG algebra structure unless you just get down and dirty and start computing and see if you can make it have one. Okay, so in fact, it doesn't always. So there do exist minimal resolutions that do not admit a DG algebra structure. Resolutions of a ring, of an algebra over another ring. That do not. So Lucho found, Abramov found the first examples like this quite a while ago. And also Hemas Srinivasan found some that were smaller and nicer in the sense of like at the limiting edge of what people thought they could, whether they could exist there, and showed that they can't. And Katan found some interesting examples much more recently also. All of these are interesting. Okay, so for one thing, you can't always have one. But on the other hand, if you don't look at a minimal resolution and make your resolution a little bigger, you can always have one. So, but there always exists a resolution X of R. Not minimal, sometimes, with a DGA structure. Okay, so we can build resolutions like that, but they might not be minimal, which might cause a problem later, but that's okay. Are there any questions so far? Then I will tell you Shrikant's result and show you in the picture how his resolution goes. I had a bar resolution. I took a ring, you take R, algebra A over K, and then you have this natural complex, and all the differentials there are just keep multiplying adjacent elements. So you multiply the first two elements, minus you multiply the second two elements, minus plus you multiply the next two elements, and so on. And it gives you a natural complex and so on. So how can we put these together? But it was too large for a commutative algebra. Okay, no questions? Little questions? Okay, let me put this one up. All right, so theorem. Iyengar, this was one of his first results. Again, let M be an R module, and R is like Q mod I. Q doesn't have to be regular for this part of the talk, but I mean, you don't even need this, but okay. M squared, let's do that anyway. Yeah, I don't know why I read that. Okay, so now start resolving these guys over Q. So resolve the ring over Q. Resolve the module over Q. And what we want is to resolve the module over the ring R, which could be difficult. But if Q is something like a regular ring, polynomial ring, then finding the resolution of the ring and the module over Q might be easy. It's at least finite then. Okay, and so calculatable. So perhaps X and Y are calculable. But together, this is going to give it a resolution of M over R. Okay, so taking these two, so choose them such that this is a DG algebra. We want X to be a DG algebra, and we want Y to be a DG X module. And if you just make them a little bigger than the minimal, if necessary, then you can always assume that this is true. And I want to take yeah, yes, okay, yes. So such that it's graded commutative. Graded commutative, yeah, so let me say what that means. Graded commutative, which means that A times B, two elements of X, are the same, is equal to -1 to the degree of A, degree of B, times BA. So that's -1 to the degree of the element A and the degree of element B. So if you take two homogeneous elements in here, so in some xi, I and xj, you want them to commute up to sign. So you want all the even degree elements to commute with everything else. And you want all the odd degree elements to anti-commute. Two odd elements will give an odd number here, anti-commute, which is like they're acting more like exterior things in an exterior algebra would. Okay, so we need that too, but that's also easy to achieve by adding, essentially you add, one way to do it is you add polynomial and exterior variables to kind of until you kill homology enough and you have a resolution. So one can get these two resolutions. And they're all supposed to be Q-free. Okay, so you take those. And then we're going to make a bar complex out of it. We're going to put the module on the right, but the module, we've replaced it with a Y. And we're going to put the factors of the ring, before I call the ring A. So it's going to be X. Instead of putting R's, we're going to put X, 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 and make a bar complex. So, and then also we want the reduced one, so I have to reduce the middle factors a little bit. So let's set X bar to be a shift, a homological shift. So shift of +1, homological shift, so that it's higher. I'll just say X mod the Q that's sitting in degree 0 produced from the 1 in there. I mean, essentially, this is the shift of X plus if the degree 0 piece is Q. So when you start resolving R and Q, and you can map the first X0 is mapping Q onto R, you can just take Q, so a rank 1 module in degree 0. So if so, then you just get rid of the rank 1 and you just have the positive degree parts of the algebra. Okay, so in other words, I've got rid of X0, that's all. That's why there's no X0 in this picture here. Okay, so you do this, you form a bar complex, and it's a resolution. So let me write that. So his result is then, so I'll just call it B for now, but it's B of R X Y. So this is a complex whose pieces are R, tensor, and then you have a bunch of factors in the middle, X bar, tensor together n times, say. And then tensored with the Y at the end. And this is given a differential, which I will describe in a second. Okay, then this thing is a resolution, is an R-free resolution of M. Oh, but I have to tell you the differentials. So the differentials are the classic differentials of the bar resolution and but bumped up like by Cartan by various people to include the internal differentials of X and Y as well. So let me say where the differential is now let's say differential prime plus differential double prime, where differential prime is just the internal differentials of all these complexes. So on the copy of R, the ring, these right here are free Q modules. So I've just tensored with over Q. Oh, all these tensors are over Q. I should have written Q. So now these are free Q modules and they're tensored down to R. So this factor it's lost a role. I'll explain in a second. But so on that, nothing much happens. But you take the internal differentials on these complexes. There's a bunch of complexes that have been tensored together. So they have a big differential coming from all the tensor factors. So I'll just write differential of the rest of that stuff. X bar tensored up n times tensored with y. I'll explain in the picture in a second. And then the second part is really called B. It's called the bar differential. And that's where you multiply. So this is where you multiply adjacent elements together. So it takes R, x1 bar up to xn, y, and sends it. So this means R tensor x1, tensor xn, tensor y. I've dropped the tensors and written bars. Okay. And so you just do all the adjacent products, but when you multiply by R, x1 lives in positive degree because we chopped off the degree 0 piece. Then multiplying that by something the ring is just sitting in degree 0. You get into a higher degree and the ring, there's nothing there. So this first product disappears for the reduced bar. But the other products are like R. Well, maybe I'll just write the sum over I of R times ... multiply xi by xi plus 1 bar ... with a y, tensor with y. And then the last, so you go over all I and you multiply all the adjacent factors together. And I forgot something very important. This is all with plus or minus signs. And then lastly, you're supposed to multiply xn by y. So plus or minus R x1 ... up to xn minus 1. And then you multiply the xn by y. So again, the x is an algebra. We've replaced R by a DG algebra that's something nice and finite dimensional, usually and free over Q if Q is regular, and replaced M by Y, but X is an algebra and Y is a module over X. So you can do these products. Okay, so that's the whole statement. And now this is actually much smaller because usually when you build a resolution of a finitely generated module, all the pieces are finite rank over Q. So every one of these is finite in each degree is finite rank over Q and becomes a finite rank R module. So this is now a finite rank resolution, which was not true before. Okay, and let me draw a picture of it because like this is a little too crazy. And then I think that's when we're gonna take a break. So, okay, so what do we have? We have all possible X's and Y's tensored together. And then they're just tensored down to R to make them free over R instead. So we're gonna ignore the tensoring down to R. I'll just put it over on the side. Okay, let's look at what modules we get here. Now, don't forget that X bar is shifted in homological degree. So for example, X sub 5 actually lives in homological degree 6 now. Okay, the Y on the other hand is not shifted. Okay, so we have Y's and lots of X factors, but all the X factors count as one more degree than they were before. Okay, so in homological degree 0, I just have that. In homological degree, I just have a Y1. Then you start having X's. The resolution X in degree 1 now has the homological degree 2. So 2 plus 0 is 2. So now we're in homological degree 2. And these are the only things we have. So the direct sum of these two modules is what we have in degree 2. Okay, and in degree 3, we have Y3 We could have an x1, which is really degree 2, and a y1, 2 plus 1 is 3. Or they could have x2, which is really degree 3 now, plus 0 is degree 3. So this is what's in degree 3. I'm going to erase all these direct sum just because they make a mess. Okay. And then here in degree 4, you have several things happening. But now it's the first place where you start getting more x factors. Because x1, we cut off x0. x1 is the first thing we have. And x1 has degree 2. And 2 plus 2 is 4. So in degree 4 is the first place where you see 2 x factors. Okay? So this is what makes up the resolution in homological degree 0, 1, 2, 3, 4, etc. And then what are the differentials? So again, x and y are entire complexes, and these are the graded free modules in the complex. Okay, so we have internal differentials from all the complexes, and we have products of adjacent things. So, okay, internal differential on y gives me horizontal arrows in my picture everywhere. See, I'm just making the y is going down in one homological. So these are all the differentials on y. Differentials on x, let's see. Well, x1 goes to x0, but we got rid of x0. Let's see, x2 goes to x1. So x2 tensor y0 goes to x1 tensor y0. So that's a differential in x. Here, x2 goes to x1 tensor with y1. That's a differential in x. X3 goes to x2. And these differentials of the x1s go to x0, which we got rid of. So those are all the differentials, internal differentials in x and y. And now you get all the bar differentials, which are products of adjacent things. So y is a DG module over x. So you can multiply x by y and end up in y. So you end up in y1, which is right there. So the product goes here. So this is a multiplication. I'll just call it m. Multiplying x1 and y1 together, you end up in y2. So that's a product. And that's a product. X2 times y0 is in y2. So that ends up there. X2 times y1 is in y3. That ends up there. So all the pink ones are multiplying adjacent factors. X3, y0, you end up in y3. Okay, here comes the weirdo. There are two things you can do with this. You can multiply these two adjacent factors and end up in y1. So you have x1, y1, which is, well, I'll do this. I mean, this is still multiplication, but I'll use a different color. It goes here. It's another multiplication. And then you also have x times, well, maybe I'll make that, okay, fine. There's no reason for the color. And x1 times x1 is an x2. So now I can also end up here. Okay, so it's just a big mess, but it's not that complicated. And it's a finite rank free module in every degree resolution. If Q is regular, you can even build one with this algebra structure and then sort of soft truncate it and after its projective dimension, and you will get at least well, in the local and graded case, you will get a finite one of these. So all these things are, all the x's and y's keep ending, but what happens is you get more and more tensor factors, so it keeps going forever, possibly. Okay, or I mean, it will keep going forever. All right, so that's one universal resolution. And when we come back from the break, I'll give you a different one.
Thank you, Claudia. We have a 5 minutes break.
Okay. Oh. Okay.
We have another 40 minutes.
Yeah, okay. I'll try to, I can just cut some things if I have to. Okay. Well, I don't know if it is. Is this making any sense? Okay, good. I can't tell at some point, you know? Okay. Good. Okay, I'm gonna start again. So I defined a DG algebra and forgot to say what a DG module is, but you can look it up. It's kind of the same thing. All right. And I mean, it's not that hard. It's okay. You get, maps from X tensor Y to Y, chain map, and such that it makes Y into a module, the direct sum of the parts of Y into a module over the direct sum of the parts of X. Okay. I also was going to give a one-line proof of Shrikant's, which means I'm skipping most of the stuff in Shrikant's paper. So the idea of Shrikant's proof is that if you do the bar construction of X, Y, then that is already what was being done in the 50s, even in the DG setting. And that is a resolution. So this is like looking at X factors, and then let's take reduced factors, tensored up n times, and Y. Then that is a resolution of M, of Y. But you kind of want a resolution of M, and you want to get back down to Earth. And so essentially, Y is quasi-isomorphic to R. So she replaces the X by an R and has to do some work with filtrations and show that then you get a resolution of M. All right. So, but I'm gonna skip all that. All right. Okay. Second part of the talk, I want to talk about a comparison of the bar resolution with another classic resolution, but one that is slightly less well known. So I want to tell you what that is first for a while. So this first part of the second part of my talk is about bar versus Eagon. So I need to tell you a bit about the Eagon resolution. And if you want to read about it, the reference to sort of where it's, I mean, they attribute it to him, but the reference that there is to read about it at all is in Gullikson and Levin's large manuscript that is sort of uniquely their large manuscript. Anyway, so what is this resolution? So I'll tell you a bit. So it's of the residue field. So the module that is being resolved is just the residue field. There have been extensions. So for extensions, some appeared in the work of Rahmati. Driuli and Yang. Okay, but they're a little off topic from how I'm going. So we do M is K, let K R be the Kazoo complex on minimal generators of the maximal ideal of R. And then you look at Kazoo homology, and you take a set BI, which is B sub I. So we're going to look at the Kazoo homology, and apparently this is enough to know that is enough, well, plus some Massey operations, is enough to really understand the Kazoo homology is enough to write down another resolution. So, all right, so this is a set of cycles in KR. So let me continue right here. In the Kazoo complex, whose images form a basis of the Kazoo homology, the homology of this Kazoo complex. And I should say for I forgot to say for I bigger than 0, so we don't want the 0th one. And that's a finite dimensional vector space. And so you take a basis of it and you kind of lift this to a set of cycles. And actually I'm lying a little bit. You might want flexibility and choose a slightly different set of cycles for Massey operations, which I'll say in a second. But anyway, you have a set of cycles. Then you let, you take this set of things and you make a free module out of it. So which is going to very counterintuitively to me called V, which for me is usually a vector space, but It's like you've taken this vector space and bumped it up to a free module. So this is now the free R module on the set BI. So we take the Kazoo homology, it's a vector space, bump it up to make it a free R module. And then also shift the degree by +1, which should look familiar from the bar thing. Okay. Then there exists an R-free resolution of K of the form. So I want to, so the individual things in the thing look like E stands for Eagon. They look like sums of, direct sum of this Kazoo complex on R, say in degree J. So pieces of the Kazoo complex tensored with these sort of Kazoo homologies bumped up to, so I'm going to do V sub I1 plus 1 tensor V sub I, whatever, T plus 1. So things like this, which looks a bit barish, right? And the differential is complicated. Oh, sorry, the sum, yeah, the sum is over, thank you, J plus the sum of the I sub L plus 1s over all L. All that equals N. So in other words, K sub J is considered to be in degree J. These are in degree this plus 1, this plus 1. So the sum of the degrees is to be N. Yeah, but then I wrote plus 1 here, which is not, oh, it is standard. So, but some people call this I1. I'm not calling it I1 because I felt like calling it I1 plus 1. I mean, I1 is just an index, so. But I still, this is still what people call VI plus 1. They usually write VI is VI minus 1. I don't know. I decided I like this better because it matches the bar better. Yeah. So it's still the same definition of V sub blah. Just, okay. So the differential here is, to say the least, complicated. We're still looking at it. It involves a bunch of lifts of bunches of things that do lift, but it's not clear what the lifts are of like maps of free complexes and stuff like that. Well, or maps from free objects to things. Okay, so I'm not going to tell you the differential immediately, but I will tell you the differential in a special case. The only special case in which people really understand the differential at this point. So, but the differential is explicit in one case. So for if K R, the Kazoo complex admits what's called a Massey. Sorry. A trivial Massey operation. Which I'll tell you what that is right now. So it just looks like something kind of unnatural at first glance. It's imported from topology. By Golod. And I don't have more to say about it right now, except I will tell you the definition. There exists a set of cycles, they're the same cycles B that I put there. B is the union of a bunch of BIs in KR, whose image is the basis, whose image is the basis of H of KR for the Kazoo homology. So same as what I said there. But there's something you can do with them, and a function mu from direct sum of B P. What that means is B cross B. It means ordered tuples of length P. Okay, so from ordered tuples to the Kazoo complex that satisfies some properties. So right here, I don't know, you want mu of B to be B, so tuple of one element to be itself. You want some more things, but let me write the general down. You want the differential of mu of B1 through P to be the sum of plus or minus. I am avoiding all signs in my talk. I will explain why later. For 1 less than J less than P, where you take the Massey operation on B1 up to Bj, and then you multiply it by the Massey operation of Bj plus 1 up to Bp. Okay, so you take the Massey operations you've defined so far, you multiply them together and combine them. This is always a cycle from the properties you've built so far. The question is only, oh wait, is it always a cycle? Yes, the only question is only if it's a boundary of something. And if it is, then you define the pth one. These are all shorter than p, the pth one. That way, and you keep going. So that's a Massey operation. Very not obvious what that means. And so in that case, the Eagon resolution, which I have erased, has a nicer differential. Then you can take the differential on the Eagon resolution of an element of the form y tensor B1 tensor B T to B. Well, you want to differentiate y because y is in KR in the Kazoo complex, and these guys are all, each of these is in the they're in the other factors, which are called V, the V's. V tensored up T time. Okay, differential of y, because that is a complex. The V's are just weird free modules, which have no differential. So we're just going to differentiate y. And there's a lot like bar, but like stuff is missing. So we can differentiate the y factor. We can also multiply adjacent things together. But we have no product. V is just this abstract thing. But we do have a Massey product. So, so plus or minus the sum over all j of leaving y there and multiplying it by the Massey operation on a bunch of the b's. So b1 up to b sub j. And then giving up and putting the rest, leaving the rest as tensor factors. Bj plus 1, dot, 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 dot. I'm not going to put the rest of the factors. Okay. Those are the only products we have, very few. But this is the differential. It makes it a complex. And this is a resolution, which I already said. So this is a resolution of K over R. All right. So now you're wondering, when do we have, what is this Massey thing? So it looks a bit horrible. It is horrible, but it is related to some sort of fundamental properties of the ring. So Golod proved long ago, and there have been many new proofs of this also since then, that the Kazoo complex on R has such a Massey, so it admits a Massey op. Oh, I keep forgetting to say the word trivial. A trivial Massey operation. Massey op. If and only if R is Golod. And now you might say, what is Golod? And I could define it. I'll say the following. Golod, a ring is Golod if K, the residue field has extremal, this is kind of a circular definition, but anyway, has extremal Betti numbers. And in what sense extremal? There's some upper bound. Essentially, what this means is equal to those in the bar resolution. Those in a bar resolution, okay. Could write a Poincare series version of it, but I think I will skip that. Essentially, Golod rings are the ones for which the bar resolution is minimal. So one does have these Massey operations at times, and there are other characterizations of Golod, and there are rings that everybody knows are Golod, so these things do exist and so on. There are other ways to figure out that something is Golod, possibly not equivalent, although sometimes equivalent. I'll mention one more thing in a minute. But this does happen, and then when it happens, you get these mysterious Massey operations. Okay. Oh, and one thing that all of this implies, by the way, is that the Kuzul homology, if you take the positive degree parts of it and you square it, you get 0. So the products, well, Kuzul complex has products. It's a DG algebra. The homology inherits an associative product. If you multiply any two cycles together representing, you get something 0 in the homology, you get a boundary. So that's the first step in getting a Massey operation, and then continues from there. So that's related to Golodness. So I'll say more in a second. Okay, so what I want to talk about is how do these two resolutions compare? So comparison. Okay, so first place, take a look at the picture. Many of these maps are no longer there. So maybe I'll just cross them out. Where's the green? Okay, you can no longer multiply, well, you can multiply those. You can no longer multiply, there's no differential on the, okay, so now the Y is now standing for the Kuzul complex on R, which means we don't really have to tensor down to R. And the X is now standing for these V's. Okay, and if you make that substitution, this picture is exactly what you see for Eagon. And a bunch of the maps are missing. So the vector space V bumped up to a free module has no differential. So all the differentials on the X's, which were like this white map and this one here, and a bunch of the diagonally white maps are all gone. And also a bunch of products between the X's are gone. So this product between the X and the X to this X is gone. So lots of maps disappear. But a new map appears, which is, oh, what's gone? The Massey operation, oh, here it is. The Massey operation, so the bar construction only multiplied adjacent things together, two adjacent factors. The Massey operation is of a bunch of adjacent factors at once. So for example, here, well, so that's not new. So the picture is not big enough to see the new maps. Okay. Yeah, if you have 3 X factors, you start to see new maps. So, all right. So they sort of look similar, but not the same. All right. All right. So let's look at a setting that comparison of the two resolutions. So here's the setting for both. So first place, we have to take the module to be the residue field because that's the only thing at the moment that Eagon resolves. For the bar resolution, we need resolutions of R and the modules, so Q-free resolutions that need to be DG stuff, right? So DGA and DG module over X. And then, and by the way, since we're resolving the module K, since this is just K, what resolves K over O? I should take Q to be regular. So, and R is Q mod I, and I'm going to take Q to be regular. And again, I have either local or graded ring. So what resolves it? This is the Kuzul complex on the maximal ideal of Q. I'll just write M sub Q. on minimal generators of the maximal ideal of Q. So I'm going to call that KQ, or maybe just K sometimes. And notice if I take Q, and I tensor it down with R, I get the Kazoo complex on the maximal ideal of R. Oh, I should have said I is contained in the maximal ideal of Q squared. Then the Kazoo minimal generators of the maximal ideal of either of these rings have the same. The images of the ones in Q give you maximal ideal in R, and this is true. Okay, so so that's the setting that is true so far, true for both to exist. And but I'm going to also assume, so that I have a Massey, well, for the Eagon, I also need to assume that R is Golid in order to have a Massey operation. But I'm also going to assume that X and Y are minimal resolutions. Okay. Assuming all that, not anymore. Okay, assuming all that, so it turns out, okay, so note you get several things. One is that you get that the products on X, at least in positive degree, are minimal. Namely, they land in the maximal ideal times the thing, and that's to do with Golidness. And the same for X plus times Y, contained in MY. You can, if you have a DG algebra product on X that has this property, it's easy to construct a Massey operation by zigzagging through an isomorphism that I'm about to give you. But the converse is also true. If it's Golid, so it has a trivial Massey operation, then it's also true that this is, but that's not as obvious. So, but this is something that's true. Okay. At which point we pause and we say, I'm taking minimal resolutions, but also the products in the DG algebra are minimal. And these are all the differentials you see in the bar complex. You see differentials within X and Y, and see adjacent products. All the maps are minimal in the bar resolution. So that tells you bar resolution is minimal. So, and this gives you that the bar resolution is minimal here. We don't really strictly use it, but it's true. Well, we use this stuff, but we don't. Okay. And then it's also true that the image of the Massey operations is contained in the maximal ideal times K, or K. Oh, I should say KR. And that will tell you that the Eagon resolution is minimal. So these are two minimal resolutions of the residue field. So they have to be the same thing, right? And it gets even nicer than that. You can even see from the picture, it's the same picture. So what's the correspondence between the parts? In fact, you can see that they have the same ranks directly. All right, so let's look at X tensor Y. So X is a resolution of R, and Y was a resolution of M. Okay, and if we take this homology, we're just computing a Tor. This is tensored over Q. Well, these are all Q resolutions. Okay, so if you, one of these is a Kazoo complex. Wait, M is K. M is M, which is K for us. So this one here is really a Kazoo complex on the ring Q. Okay, so we can get to Kazoo homology by replacing X by its quasi-isomorphic R, because the other tensor factor is free. This is isomorphic to R tensor KQ, which is really just homology of KR, which is what we were calling V. Maybe put subscripts. So HI, and this was called VI plus 1. Okay. On the other side, if I instead replace the Y by K, because it's quasi-isomorphic and this left guy is free, I get the homology of X tensor with little k, the ith homology, but X was a minimal resolution. So now it has no differential if I tensor with K. So now the differential is 0. So it's not, you don't have to take homology, it's just xi tensor k. Okay, so I should not have written V here. I'm sorry. V is the free module, not the vector space. It's called V, it drives me crazy. Okay, so anyway, the dimension over K of this is the rank of V, I plus 1. And the dimension of K of this is just, I mean, you've got a free module and you tensor it down, the vector space dimension is the same as the rank before that. So it's the rank of xi. So that means that xi, oh, shoot, this needs to be an R module. I mean, it is an R module. So I should say xi tensor R maybe. Well, fine, xi over rank of xi over q. Okay, that tells you that xi, if I tensor it with R, so that it's a free R module instead, is actually the same as this other free R module. So these are the same module, the same free modules. So every piece in both pictures is isomorphic to every other piece in the other resolution. But the differentials seem to be very, very different. So, yikes. So theorem is there is a map between them that resolves this question. And this is with the first three authors that I listed, Briggs, Rahmati, and Yang, is that there's, okay, so first we have to do some lift. First, let's lift the Massey operations. So we have a set B, well, it's crossed with itself P times, goes to X tensor. Oh, no, sorry. The Massey operation goes to the Kazoo complex on R, which is really the same. Oh, let me erase the bottom part. Kazoo complex on R, which is really R tensor K, by which I mean the Kazoo complex on Q. But we're trying to get to the bar resolution, which had, this is also what we were calling Y. But we're trying to get to the bar resolution, which has X's and Y's, not just R's and Y's, but X is a resolution of R. So this is the same as X tensor Y. And so one can lift, let me put a dotted line. And one can lift and get a kind of a lifted Massey operation. All right, once we have that, we can compare the two. So the Eagon resolution, which is the direct sum of the Kazoo complex on R, tensor with a bunch of copies of V's. I'll just put V tensor N over all of them. That's not really how they're split up in terms of degree, but I'll just write it this way. There's a map phi, which I'll describe in a second, to the direct sum over all T of the Kazoo complex on R, tensored, and now we lifted the Massey operations to here. X tensor Y, a bunch of times, so tensored up T times. Okay, and then one can arrange, there's some obvious maps here that I'm not writing down. One can move the Kazoo complex. So the Kazoo complex on R is really, KR is really the Kazoo complex on Q, which is what we're calling Y, tensored down to R. So it's really a Kazoo complex on Q, it's just tensored with R. So we can leave an R at the beginning, move the K's to the end, which are really Y's, multiply all the Y's together, rearrange everything, and we can get to, and then go to the reduced copies of R's, and you can get to R tensor X bar, tensored up T times, tensored up with K, which is KQ, which I'm going to write as Y. There. T. Okay, so there's a map, which I'll give you in a second, such that if you compose with the obvious isomorphisms of modules, these are not thinking of them as complexes. This map psi is an isomorphism of complexes. So, and this was the Eagon. As you know now, this is the reduced bar, which I called B. So the Eagon resolution is the same as the bar, but I need to give you the, oh, and we have not quite figured out the signs. We're getting close. So I'm going to say, let the characteristic of K be 2. Okay, we're getting there, but we haven't, it's not quite, anyway. So the plus or minus signs are still messed up, but let me tell you what phi is. And then I want to tell you a quick 5-minute different application, a different thing. Where phi of y tensor b1 tensor b something bn is the sum of plus or minus. So oh shoot, I think this is wrong. No, it's fine. Tensor, the Massey operation, the lifted Massey operation, which actually lands in X tensor Y, of a bunch of the B's. So I'll just go up to BI1. Tensor, the Massey operation of BI1 plus 1 up to BI2, and tensor, and then you keep going until you run out of stuff. Mu of some stuff up to Bn. So you take all the B's, divide them up into subsets, because I mean to pick a partition, and apply all these lifted Masseys to them, and over all partitions, and that's the map. So somehow this map converts between something that has just Massey operations happening on the first bunch of factors to sort of spreading them out and happening everywhere, but at the same time somehow just being adjacent multiplications. Very weird. So phi is very weird because it looks very pretty, but it's not even a chain map. Okay, but by the time you get to reduced bar, psi is a chain map and an iso. So the two universal resolutions are isomorphic. Okay, so that's just resolving the residue field, but also I made a big assumption that X and Y are have DG structures, and we're working on the A infinity case too, so we don't have to assume anything because every minimal resolution has an A infinity structure, and then there are some corresponding similar things you can do. And so we're working on that, and that's using, instead of the bar, so A infinity on the minimal resolution, we're going to be using, we haven't done it yet, we're using Jesse Burke's A infinity. Well, he shows that you always have A infinity structures and A infinity bar resolution. And show that that's the same as the Eagon, because Eagon still exists then. So I don't know how much time I have. I wanted to mention a little bit of work with a different person. 5 minutes. Okay. All right. Two is an application, not of the first part, but an application of bar resolutions. And this is joint work with Michael DeBellevue. And I'm taking the same type of situation that, R is Q mod I, and N is an R module. And Dow and Eisenbud proved a very interesting result, that if the Birch index of a ring, I'm assuming it's a depth 0 ring, so the classic Birch index, which I'll describe to you in a second, is at least 2, then the syzygies, the R syzygies, the I syzygy of the module M, doesn't even matter what M is. This is a property on the ring. The property on the ring causes all modules eventually to split as a direct summand a copy of the residue field. So plus possibly stuff, it might be nothing, but it's usually stuff. So this was for I equal to, it didn't start quite right away, I equal to 4 or 5, and all I at least 7. So, so let me tell you for a second what the Birch index is. Actually, okay, I want to tell you for a second what the Birch index is. So if you're looking at the ring and it has depth 0, it has a socle in it. So the socle is all the stuff that gets multiplied into I, or into 0, into I by the maximal ideal. It's the vector space. So it gets multiplied by the maximal ideal into I. So here's the maximal ideal, and this is the stuff, so this is really the socle, and it's the stuff that gets multiplied into M. So this is inside of Q, it's all the stuff that gets multiplied into M, so it's a lift of the socle. Okay, of course, that contains I. I gets multiplied into I by the maximal ideal. And that contains stuff in I that are not minimal generators. So we're going to distinguish between minimal generators of I and non-minimal things, and things that are not minimal generators in I. And so you go and you multiply by some element by the maximal ideal, and you land, whoops, you land in I, right? Okay, because it's a socle element. But sometimes you don't, and you land in I, but you land deeper in I, you don't get a minimal generator. And what the Birch index is measuring is how many minimal generators of maximal ideal multiply you to generators and don't multiply you further, which is related to some other things as well. So the Birch index is sort of the quotient of the things that, so it's the dimension, the vector space dimension of the things that multiply the socle in, and versus the things that multiply you deeper in. So that's called IM colon the socle. So I colon M, whatever. That's the stuff that goes further in. So we're counting the stuff that does not go further in, but not the stuff. We're counting the things that multiply it, not further in. So you're counting the minimal generators that kind of just look like socle elements times a minimal generator maximum. Okay, but so what Michael and I did was we gave a different proof of this using the bar resolution by finding some special cycles that just keep appearing and appearing and appearing and appearing in the bar resolution, and actually are giving you these summands that split out. Okay, all right. So this Birch index being at least 2, it gives you some that there exists an F in X2, which is again, X is the resolution of R over Q. A DGL, or let's say a minimal resolution, which you can put an A infinity structure on. So there exists an F in X2 that's actually a basis element, but it has this weird property that the differential of F is if you multiply it by, this is some special socle element that is to do with which thing got multiplied into where, is landing in I times X, but it's not landing in MIX. And so that property enables us to construct lots of cycles in the bar resolution that generate these copies of K, these summands isomorphic to K. And they look pretty simple. They just look like the socle element. And then in the bar complex, you take the special F that you find that comes from the Birch index 2, and then you just put any other junk you want, E. And then, okay, I'm not explaining what psi of E is, but it's E in the other resolution, like an image in the other resolution, where just E is something, a basis element of degree of in X1. And Or sometimes, so that's like for certain, an even something or odd really, syzygies, and the other ones look like, so I'll just put or. The other ones look similar, like E, F, E, 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 I of E. One of these has odd degree and one has even degree. Because the things in the middle get bumped up in degree. So these, even though that was degree 1, it's really degree 2. So this is only differs by even. So these two are, this causes it to be even or odd. Okay, whatever. So all of these guys, oh my God, I didn't write this one fully. Minus some more stuff. S1, E, F, E, 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 psi of E. Sorry, this one, or this one, these are constantly cycles that are, we put a Sock element in front so they're killed by M, so they give you a copy of the residue field. But they split out because these guys are basis elements and because of this property that the Sock times this differential of this is not landing too deep. So somehow in the bar complex, you can sometimes see things that are kind of universal. It has nothing to do with the module you're resolving. It just has something to do with a part of the resolution X. A small part in degree 2 of the resolution X caused everything else to happen later in the bar. Okay, and that's all. And so now we get it coherently for all I bigger than 5. And in the Golded situation, we get actually exponentially many going up. In the other case, we have to take the bar and we have to project it to the minimal resolution. So we lose all these. We just show that one of them survives in the minimal resolution. Okay, done.
Thank you. Are there any questions?
Here's the
5. Oh, I forgot. So this has a degree. This is an X2, but it's inside the bar. So it's really got degree 3. This is an X1, so it's really got degree 2. But actually, you could just leave all of these out. So you'll have a degree 3 element. And this is one more. This would be degree 1 more. Right. So in the Gola case from degree 4 up, I now don't remember if this was the Golded or not Golded. This was the A infinity version or not. Yeah, so this now has degree 1 plus 2 is 3, but now it's therefore you bump it up. So this has degree 4 and this has degree 1, and this is giving, yeah. But I feel like I might have messed up and written the wrong cycles that are, so there's the DG situation and then there's the, in the A infinity case. Did I write the wrong ones down? Because this looks like it would have one of degree 3, 4, 4. In the Gola case, we do get this. Yeah, they can get rid of, oh, you need to keep one of the E's. Thank you. Because then we're going to put it here. Yeah. Yes. So the smallest degree is not going to come. This will be degree 5. Thank you. The smallest one is degree. Yeah. Yes, 6. Right. And this, I forgot about the psi of E, which is another one. Yes. Yeah. And that kind of shows you why they shouldn't. Well, okay. There's no easy way for them to show up earlier, but they do show up earlier, right? Oh, the second syzygy always, aha.
Okay,
Yeah.
sorry. In K, they show up from.
Right. For general modules, not, yeah, so there's like yeah, okay. So this is kind of the best you can do in general, yeah. And then, of course, various modules, other things happen. Well, anyway, people are also studying what other summands split out, but I'm not part of, I don't know, that seems very hard to me. But there's progress, recent progress on what other summands exist as well. Any other questions? All right, sorry I ran over.
Thank you very much. And the seminar next month will be strictly online.
I'm sorry, I